In this video, we're going to learn how to create a confidence interval for the sample mean. If you remember from our first video where we saw the central limit theorem and the distribution of the mean, we know that a sample mean that we call x bar of a sample size n from a population with population mean mu and population standard deviation sigma is distributed approximately normal with mean mu and variance sigma squared over n. This is from a result called the central limit theorem. Mathematically, this can be written as a probability. The probability that x bar is between two specific limits is 95%. We know that because the normal distribution has very specific properties. We can choose two numbers such that they contain 95% of the probability. In this example, mu is 28.66 and sigma is 9.02. That's the example from the first video. So samples of size 50 will fall inside an interval. The interval is between 26.1 and 31.2. And that's the interval that covers 95% of the probability mass of the normal distribution. So we take samples, and most of the time they will fall in this interval, but not always. Okay, one time out of 20, you're going to get a sample mean, then it's going to be too extreme, too different, and it's going to fall outside this interval. But most of the time, or exactly 95% of the time, if you do it many times, you're going to get sample means in this interval. If we have this interval, and we know that we take sample means, and those sample means will fall 95% inside it, we can also say the following. If we choose one of the means that fall inside the red interval, the interval which is constructed, and we center an interval of the same length on that mean, that new interval, the blue one in the picture, will contain mu, the population mean. That is just a mathematical reality. I just shifted the interval to center it in one of the means, and it contains mu. If I choose another one, this is a very extreme mean from a sample, and I center an interval of the same length as the red one, it will also contain mu. Barely, but it does. If I choose one of the means that falls outside the interval, and I center a new interval of the same length on that mean, that interval is not going to contain mu. So the reason I'm doing this is to make the point that the statement we just made, that the mean is going to fall within a very specific interval according to the normal distribution with 95% probability, it's equivalent to say that if I take successive samples and compute the means, I can construct intervals according to these numbers and using these numbers such that with probability 95% contain mu. Okay, these two statements are mathematically identical because you can go from one statement to the other one by just moving the terms around. If you're not sure about this, pause the video and try to move the terms around to go from one expression to the other one. We started with the red box here, a statement about where does the mean fall. Intervals that will contain new sample means. Okay? If mu is 28.66 and sigma is 9.02, the new sample means of size 50 will fall inside a very specific interval. This interval is mu minus 2.56 and mu plus 2.56, or 26.1 and 31.2. That interval 95% of the time. That statement is equivalent of saying if mu is 28.66 and sigma 9.02 and you draw new samples of size 50, then the interval x bar minus 2.56 and x bar plus 2.56, notice that it's a different interval, will contain mu, so the number 28.66, 95% of the time. Okay? Notice that to make the second statement, we don't need to know mu. Okay? We can just probabilistically say that the intervals will contain mu, but we don't need to know that it is 28.66. We only need to know sigma. Okay? So, I'm going to read it again. Sample of size n equal 50 from a population with sigma 9.02 will generate means such that the interval x bar minus 2.56 to x bar plus 2.56 will contain mu in 95% of the cases. And this, ladies and gentlemen, is a confidence interval with 95% confidence. This is where we want to go. We're still not there, but this is it. Conceptually, that is a confidence interval. Okay? So, a 95% confidence interval provides a range of values centered around the sample mean that would contain mu 95% of the time if the sampling were repeated many times. So, that's the interval. This number 2.56, remember, comes from choosing a specific point in the normal distribution. So it's 1.96 times the standard deviation of the normal distribution. The standard deviation of the distribution of the mean is sigma over square root of n. So that's where it comes from. And we construct successive intervals, one after the other, and 19 times out of 20, they will contain the population mean mu. So, this is great. But we don't know the population standard deviation, sigma. I mean, in my example, we know it, but in reality, we'll never know it. What do we know when we do research? We have a sample, and also we have a mean of that sample and a standard deviation of that sample. That's what we observe, this blue box. All these other things we've been using, the whole knowledge of the distribution of the population mean, the population standard deviation, sigma, we don't observe. We don't know that. Okay, so we only know the blue box. Now, what do we notice here? What we notice is that the mean of the sample and the mean of the population, they're very close to each other. But we know that. That's the, central limit theorem and all of that. But we also notice that the sample standard deviation and the population standard deviation are also very close to each other. They're not quite the same, but they're similar. 9.02, 9.42, okay, they're not the same. But the question is, could we use S? Could we use the sample standard deviation to construct an interval? Okay, it's not such a bad idea. The problem is, are we making a mistake? So this question was studied by this person, William Gossett. William Gossett was working at the Guinness distillery in Ireland, and he was in charge of doing R&D to make better beer. More than 100 years ago, he had this problem, and he was a very good statistician, and he developed rules and a whole machinery to use S, the sample standard deviation, instead of sigma. Okay? So how does this go? We only observe the sample. So that's the only information we have. If we replace sigma by S, if we replace the population standard deviation by the sample standard deviation, we could construct an interval. Look at this interval here. We know x bar, we know S, and we know n. There's no problem. We could compute this. Now, the problem here is that Gossett realized that there is uncertainty in S is there is uncertainty. Every sample we compute will have a new mean, we saw that, but also a new standard deviation. So this S value will vary also. There is also a distribution of S in every, if we take repeated samples. So he said we need to account for that uncertainty, and the way to account for that uncertainty is to construct a wider interval. And he proposed something like this. We're going to get to a moment where this green number comes, but he said we shouldn't use 1.96. We should use a larger number. And that's the idea. If you want to use S, you have to use 2.11 in this case instead of 1.96. This wider interval is going to account for the uncertainty, and it's going to make sure that upon repeated replications, upon new samples, you will contain mu 95% of the time. So this, for relatively small samples, is not quite correct. So what's the idea? If you have a normal distribution, and that's a distribution of the mean, okay, x bar, remember, is a normal distribution centered at mu with variance sigma square divided by n. You know from the theory of the normal distribution, I'm sure you've seen that before, if you subtract the mean from a random variable and divide by the standard deviation, what you obtain is a new random variable, this one, that is distributed according to the standard normal. What Gosset said is that yes, that's all fine, but if we were to use the S, the sample standard deviation, then we cannot claim anymore that this is normal, because this S has its own uncertainty. And we have a ratio of two things with uncertainty, x bar and S. And he said, he proved it, that this is distributed with something called the T distribution. By the way, this is called the student T because Gosset signed his article as student, because he wasn't allowed to publish his research because he was working for a private company. Anyway, what is this T distribution? It's something that looks very much like the normal. If you see here, the normal is drawn in red and the T distribution is drawn in blue. And you can see it's symmetric, has similar shape, but you see a difference already. You see here, the tails, or we call the tails of the distribution, are heavier for the T. There's more mass next to the extreme values, and there is less mass in the middle. So you can imagine this as being a normal distribution with what we call heavier tails. What are the consequences of this? This allows for the more extreme outcomes. So, for example, an outcome close to the tails is way more likely under a T distribution than under a normal distribution. Okay, so the T distribution approaches zero more slowly than the normal distribution. And this has consequences. On the left, we have the normal distribution, always in red. And we said that we know from the normal distribution that in order to get 95% of the mass, I need to create an interval in very specific points, namely minus 1.96 and 1.96. Okay, that ensures that we cover 95% of the mass. Because the T distribution has more mass outside and less mass in the middle, in order to cover 95% of the mass, we need to go a bit further. Okay, look at this is going beyond 2. So this is drawn for a very specific T distribution. T distributions are described by something called the degrees of freedom. And for this particular T, you have to go a bit outside. I think it's 2.2 for 10 degrees of freedom. Okay? But what does this say? It says that if we were to construct an interval for the normal distribution, you see it now in red, and we were to construct an interval for the T distribution, the interval for the T distribution is going to be wider. Okay? And as we said before, this accounts for the uncertainty that using S introduces into the creation of our intervals. Very well. So let's get these things together. We start with data. Okay, that's our sample. We compute the mean, the standard deviation, and we know n. So what do we need to do now? Well, we need to build the interval. How do we do it? We just do it as we did before, but instead of using 1.96, we use this new number, 2.11. How does this look like? If we introduce the numbers, this is the result, and eventually you get this interval between 24.54 and 33.91. Actually, when you report an interval, because this is already giving you this wide range of uncertainty, you can say simply 24.5, okay, and 33.9, and that's already you're giving too much credit to this last decimal. So what are we missing? Where is this 2.11 coming from? This comes from a table. So one of the things Gosset did when he developed this theory of the t-distribution, he said, okay, let's come up with these values. So in a table, you typically would look at what is the value to use to compute 95% intervals. And then you would find the value that corresponds to your degrees of freedom. Okay? So here I chose 17. Can you guess why? Yes, because of this. When you use the t-distribution to compute an interval, you have to use a number of degrees of freedom equal to the sample size minus 1. It's very easy to remember, so here's 17. Okay, 2.11, and that's the number I used. And that's it. These are the 4 steps to build an interval from the data. We're not using information about the population anymore. We have data, we compute the values that we need, we find these limits of the t-distribution from a table, and then you just put the numbers together and find the interval. That's the recipe. Everything we've been doing so far leads to this point, so you can even forget about everything you've learned and just follow these steps. Very well. We're almost there. So let's reiterate once more what we're doing. A 95% confidence interval can be constructed from a sample, and it will provide a range of values centered around the sample mean that would contain mu 95% of the time if the sampling method were repeated over and over. So the same picture we had before, but notice now that the intervals have different length. Every sample will have its own mean and its own standard deviation. So it will be higher or lower, its own mean, and the length is given by the standard deviation of the sample. Sometimes it's going to be larger and sometimes it's going to be shorter. Okay? But the important thing is that if you follow these steps, you are sure that 95% of the times you're going to draw a sample that contains the population mean. The question that remains is, what is so special about 95%? We've been using this number since the previous video, but there's nothing about it. We just use it. It's an accepted norm. I mean, you have to choose a number. 95% sounds 1 in 20. It sounds a reasonable number, but you don't have to use it. Can we create a confidence interval with a different confidence level, like 93% or 97% or 82%? Of course, yes. I mean, any number. It's just that you'll have to explain to whoever is reading your report that you're using a different confidence. So 95% is like an accepted norm, but you can also use another number. So imagine we were to compute a 90% confidence interval. Would this interval be wider or narrower than the 95% confidence interval? You can pause the video and think a little bit about this question. So 90% versus 95%. Okay, how do we think about this? Well, the 90% confidence interval, what does it mean, 90%? It means that these intervals we construct by taking repeated samples will contain the population mean 90% of the time. So fewer times, which means they're going to be narrower. Yeah. So if you want a smaller confidence, you're going to get a narrower interval. If you want a 99% confidence interval, they're going to be wider. You want to contain the mu 99% of the times? Well, you'd better get a wide interval. So here we have, again, the distribution with 10 degrees of freedom. That's the way I'm drawing it. So we have 95% and 90%. And you can see that in order to cover 90%, we don't need to go so far out into the -2 and the +2. You can stop earlier. And in fact, when you look at tables, the famous t-tables, for 10 degrees of freedom, you will see that to construct a 95% interval, you need to use the numbers 2.23. And for a 90% interval, you can just stop at 1.81. Okay, those numbers we get from tables, but this is how tables are arranged. The rows are degrees of freedom and the columns are the confidence. So we can do it again. We have the same data that we had before. We can compute now the mean and the standard deviation as we did before. Nothing has changed. But now we want to create an interval with 90% confidence. So we go to our table and we find another column where we can obtain the new limits. In this case, is 1.74. Before we used 2.1. But for a 90% interval, we have a smaller number that we can easily plug into the interval. We plug it in, we compute the corresponding magnitudes, and we obtain this interval that, as you see, it's a little bit narrower than the one we did before. 25.4 and 33.1. And that's it. That's it. Now you know everything you need to know to make confidence intervals. So, a confidence interval will contain mu with a given probability in repeated samples. That's what it is. We compute the interval by computing the mean and the standard deviation from the data, and by finding the corresponding value of the t-distribution on the table. That's it. That's the recipe. Okay? Very well. Now, you can go out, gather your samples, and build your confidence intervals. It's a powerful thing, and it's based on remarkable results from statistics. Until next time.